Hello everybody, so this is the last video associated with chapter 2 of the reinforcement learning course. In the previous video we've discussed approaches to form estimates of the value of the various actions in a k-armed bandit setting, and then these estimates can be used within an epsilon greedy policy to select actions and attempt maximizing the expected reward an agent receives through k-arm bandit procedure. Okay, so earlier we discussed epsilon greedy strategies or policies to select actions, whereas here in the current lecture we will discuss alternative policies or ways to select action, but with the same objective, which is to maximize the expected return we get within the procedure. Okay, so a quick recall: epsilon greedy approaches entail doing the following. At each time step or at each play, you randomly decide whether either you pick the greedy action with probability 1 minus epsilon, or you select a random action with probability epsilon. Okay, so either you choose the action which has the highest estimated expected reward, or you select an action random. However, proceeding in that way does not consider the extent of uncertainty associated with the various estimates. Okay, so for example, some actions could have low estimated rewards, but let's say action A has low estimated reward with high certainty. So you've sampled from action A many times and you consistently receive bad rewards, whereas maybe an action B has the same estimated expected reward, but there's more uncertainty associated with that estimate because you've sampled far less often from that second action B. Okay, so in that case, it might make sense when exploring to spend more time on actions which have more uncertainty. Okay, because if you've explored some action quite often and you know with high certainty it's bad, it's not worth spending a lot of time on it. But if one action seems bad but you're very uncertain about its true value because you didn't try it often, it might be worth exploring it some more, trying it a few more times before ensuring it's really a bad one, or maybe you were just unlucky with that one and in fact it turns out to be a good action. Okay, so you want to spend more time on actions for which your estimates are uncertain than the ones for which your estimates are certain uh, if they seem to be bad actions. Okay, so what that means is that actions, I'll read it, what's written here: actions with a low estimated value but with high uncertainty, they have more potential to turn out as good actions than actions with low estimated value and high certainty. Okay. So the question now is, how do we measure certainty with respect to the estimate of an action? Okay, so one approach could be to consider the standard error associated with our estimate. Okay, so this is something we could do. However, the approach warranted or suggested by the book is slightly different. So in the textbook, the approach proposed to consider or to integrate the uncertainty of the various estimates when choosing actions consisting using the following rule. Okay, so at play number T, the action selected is the one which will maximize the following quantity, the one which will maximize the estimate of the current reward associated with action A. The estimate of the expected reward associated with action A. Plus, here, this is a correction term. Okay, so if this correction term wasn't here, then this would simply be the greedy approach. Okay, so if this term did not exist, choosing the action which has the highest estimated value is simply being greedy. But now a second term is included in the expression where to this first term we add a constant c times the square root of log of t, the log t being the play index at which we are at right now, divided by NTA, which is the number of times action A was sampled prior to play A. Okay, so if action A was sampled very often, this n will be very large and this term will be close to 0. Okay, so here I haven't said it, but C should be a constant greater than 0. Okay, so this, if NT is very large, action A was sampled quite often, then there's high certainty about this action and this term will become close to 0. Conversely, if action A was not sampled often, then this NT will be low and this whole term will be large. Okay, so when you're selecting an action which maximizes this sum, if an action has high uncertainty, this term will be high and it's more likely that it will be sampled when trying to maximize this whole quantity. Okay, so we can see that the criteria here, or the expression here, is large either if the estimated expected reward is high or if there's high uncertainty associated with an action. Okay, so here this quantity here inside the Rmax, it's known as the upper confidence bound. Okay, so it's not a confidence interval in the statistical sense, but still this expression here, it's called an upper confidence bound. Okay, so you try to select the action which maximizes that upper confidence bound, and this confidence bound, it not only considers the expected value of an action, but estimated value of an action, but it also considers its uncertainty. Okay, so this is repeating what we just said. The larger n is, the more certainty there is about an action, and therefore the less likely we are going to sample it because we need to spend less time exploring with this action. Furthermore, if we go back here one slide, this log of t, it's not a bounded function. Okay, so as t goes to infinity, log of t converges to infinity also. So why is that important? It's because it ensures that every action, here we're going to assume that we have a finite number of actions. Okay, it's the k-arm bandit, k is finite. Having log of t converge to infinity ensures that each action will be sampled an infinite number of times. Okay, because if that was not the case, so if at some point we stop sampling from some action A, then NTA would be fixed. Okay, because not choosing A would keep NTA fixed. And then if we go back one slide, so if NTA is fixed but time goes to infinity, then this whole expression converges to infinity. So the upper confidence bound for action A would converge to infinity, and this would entail that eventually action A would be selected again. Okay, so if this term converges to infinity for some action A, then action A would eventually be sampled. Okay, so it's very important to notice that. So according to this choice, this ensures every action will be sampled infinitely often as time goes to infinity, and therefore the estimate, of the value of each action will converge to the true expected reward. Okay. Furthermore, another interesting feature of using log t, so we could ask ourselves, why not simply t instead of log t? Well, uh, one thing we have to notice is that increases in log t are smaller when t is large. Okay, so the increase between log 1 versus log 2 is much larger than the increase between, uh, let's say, log of 1,000 versus log of 1,001. Okay, so this is due to the um, negative convexity of the log. So the log function looks like this. Okay, so its convexity is negative. So you can call it a concave function. Okay, so what is the impact of this? It means that actions with lesser value will be sampled less frequently as time goes by, because eventually it's really the 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 first term here, this q, which will drive the show here, the estimates of expected reward. This term here should eventually become less important, okay, due to lesser variations associated with log of t as time goes by. Okay, so this ends the discussion about this new action selection method. So this last method, we can call it action selection based on uncertainty. And now what we will do, we will see another category or another type of method to select actions. Okay, so in all previous methods, action selected depended on the estimated value of each action. This makes sense, but what we're going to see here is that it's possible to create or consider other methods which attempt still maximizing the expected reward, but here which will not form directly estimate of actions values. Okay, so instead of action value estimates, this new method we will see next will consider what we call action preferences. Okay, so here action preferences, they're abstract quantities which don't have an interpretation in terms of rewards or expected rewards. They're just preferences, and we try to adjust preferences so to eventually have higher preferences for actions which yield higher rewards. Okay, so we will now illustrate that method. Okay, so this method will seem a bit more abstract, but eventually when we go through chapter 13, we will study more in depth the rationale about these kind of methods, and this approach hopefully will make more sense at that point. Okay, so right now it's normal that it seems a bit abstract, and like the first time I went through this one myself, I thought like, how did people come up with this? But eventually, when you go through chapter 13, this should become much clearer. Okay, but we will nevertheless study the approach. So right now we're going to see that it works, and in chapter 13, we might answer the question of how did we come up with such an approach. Okay, so in this approach, we will consider the following rule. Okay, so here our policy, which entails that which is our approach for choosing actions, will be driven by the following equation. So here, pi ta is defined as the probability of selecting action A after the first t minus 1 place. Okay, so here this is a conditional probability given all rewards from the past. Okay, I just realized that maybe this notation is incomplete because you probably would need to condition over all previous actions also. So I apologize for this imprecision. Okay, but it's let's say the right side is the information that we have obtained after the first t minus 1 place. Okay, so what we have here, so we have a policy which at step t or play t can randomly sample from the various actions with probabilities pt. And each of these PTAs, so probabilities associated with each action A, are defined as the following. So it's the exponential of HTA. So HTA, we will call it the action preference for action A. And here the subset T means the current value of the preference for the tth play. And here we divide by the exponential of the action preference, but we sum for all actions. Okay, so all these HTA, A goes from 1 to K, where K is the number of total number of possible actions. These HTA are called action preferences, and the probability to select a given action is the exponential of its action preference divided by the sum of exponential of action preferences across all possible actions. Okay, but so this is how we select actions, but then how do we determine these action preferences? What rule do we follow to determine these action preferences? So here we're going to give the formula. So right now this formula will look very abstract, but we will justify the formula in the next slides. So action preferences, they're assumed to be computed recursively through the following rule. Okay, so action preferences are the following. So at time t plus 1, the action preferences for capital AT, so capital AT is the action that was selected at play T. So if at play T you select action AT, then its associated action preference for the next time step will be the current preference plus some constant alpha times RT minus RT bar. So RT is the reward obtained at play T. RT bar is the average reward obtained for all plays from play 1 until play T times 1 minus pi T AT. Okay, so this is 1 minus the probability of having selected that action AT at play T. Okay, so this term here, it's always non-negative. It's between 0 and 1. Conversely, at time t plus 1, the action preference for all other actions than the one which was selected at time t is the previous preference, but here minus alpha times RT minus RT bar times pi t of A, which is the probability of selecting action A at the tth play. Okay, so if we have action preferences at time t, then we can select an action at time t randomly. From this action, we observe rewards, so we have these rewards, average rewards here, and then we have this incremental or recursive formula to obtain action preferences at the next step for all possible actions. Okay, and here alpha, it's a small constant which is greater than 0, but typically it's a small constant. Okay, so this tells us how to determine action preferences. So this is recursive, but at time 0 or before the first play, what values do you use? Well, you can set them all to 0 or something like that. So at the beginning, you can set up arbitrary values. Okay, you can set them to 0 or to any real number that you want. Okay, so okay, in the next slide, we won't provide the exact rationale for this, but we will try to see what happens. So, under the previous recursive equations, when action A is selected, its preference is increased if the reward obtained from that action is greater than the historical average reward, or its preference is decreased when the reward you obtain is smaller than the historical average. Okay, so let's say that historically you've always had, well, you had averages, sorry. Let's say historically you had rewards for which the average value was 5. So let's say that now you sample from action capital AT, and then for that action you have a reward of 10. Okay, so this reward is higher than the average reward you had historically, so this will increase the preference for the action which you just sampled. And then the second thing will happen, the preference for all other actions move in an opposite direction. Okay, so if for a given action you have a reward that is higher than the average, then you will increase the preference of that action and decrease the preference of all other actions. Conversely, if for some action you receive a reward that is lower than what you historically had in average, then you will reduce your preference for that action and increase the preference of all other actions. Okay, so this is what happens. Let's confirm that with the previous equation. Okay, so let's say that you select action AT at time t. Then the next preference is your current preference. Well, plus, let's assume that for now your reward is higher than the expected average. Then this quantity will be positive. Your current reward is higher than the average historical reward. And here, this second term here, it's always between 0 and 1, so this is positive. So this whole term will be positive, and your preference will be increased for action AT. Conversely, if RT is smaller than your historical average, this whole term will be negative, and you will decrease here your preference associated with action AT. Then for all other actions, so for all A is different than AT, all actions that were not selected, your next preference is your previous preference minus this term here. Okay, so here, assume you had a higher reward than your average reward. You want to decrease the preference of all other actions, which is precisely what will happen here. So if RT is greater than the average, this term will be positive. Pi t here, it's a probability. It's always 0 between 0 and 1, so it's also positive. So here, this whole term will be positive. So when we add the minus sign here, the term becomes negative, and the preference will be reduced. Okay, so for all actions not selected, if you obtain a reward higher than the average at play t, then the preference for all other actions not sampled will be reduced. Conversely, if you obtain a lower reward than the average one, the preference for all actions you've not sampled will be increased. So this is the intuition behind this formula. Okay, so this gives a nice intuition, but how did we come up with this formula? Okay, so this seems to be far from obvious. So to see that, we will first provide an alternative way of writing the previous equation. So maybe I'll rewrite the previous equation here. So we had the following. So we had ht plus 1 at is equal to ht at plus lambda rt minus rt bar one minus pi t at. Okay, so you can see that when the action A is equal to AT, then both these equations are the same, because when action A is equal to AT, this indicator is equal to 1, so we exactly recover our expression here. Furthermore, when A was different than AT, we had the following equation: ht plus 1 A is equal to ht A. Here we had, okay, I'll write it like this. The minus sign, I'll place it at the end, but this is plus alpha rt minus rt bar times 0 minus pi ta. Okay, so the minus sign, I've placed it here instead. So we can see that, again, this expression holds. So for all actions A, if A is different than AT, this becomes a 0. So it's exactly this expression, which is the one we presented earlier. Okay, so this update equation here for action preferences, it holds both for all actions A, which is for both the actions selected at time t and all actions not selected. Okay, so this is the general formula to update preferences for all actions between before play t and after play t. Okay, so let's move this. Won't be long. Okay, let's go to the next slide. Okay, so what we want to do in that framework, so now we will discuss how we found the previous equations. Okay, so what we would like to do is to adjust the action preferences for all actions. So optimize action preferences HTA for all A, so as to maximize the expected reward at the next play, at play T. Okay, so if how can I say that? A very popular approach to optimize a function is called steepest gradient ascent. Okay, so when you want to maximize a function, you can use a steepest gradient ascent. I know I'm not sure if everybody in the class is familiar with that, but the idea here is when you want to when you calculate the gradient of a function at some point, the gradient gives you the direction in which the function increases the fastest. Okay, so if you want to maximize some function, what you could do, you could select a point randomly, then look at the gradient and go in the direction when you increase the most, then compute the gradient at this new point, look at the direction at which the function increased the most, follow this direction, and eventually when you reach a maximum, what's called a local maximum, then the gradient will become zero, and when you're at that maximum, you should stop moving. Okay, so this gradient ascent business, I encourage you to have a look maybe on Wikipedia if you're not familiar with that. But I've put a footnote here to describe how it works. So in a gradient ascent scheme, you want to find the maximum x of a function f, and how it's done typically is by following this recursive scheme. So you find a sequence of points where hopefully every time you obtain a new point for that sequence, the value of your function is higher until you reach the maximum value. Okay, so the recursive formulation to get that sequence of points is the following. The n plus 1 point in the sequence should be the previous point plus here alpha n, so this is what we call a time step, which is a small quantity, times so in one dimension it's the derivative of a function, but if we're in a multiple dimension setting, this derivative becomes the gradient of a function. Okay, so what this entails is that the next point in the sequence is the previous point that is shifted slightly in the direction of the gradient, so as to try to find points where the function is gradually higher and higher until you reach a maximum. And then at that maximum, the gradient here, or the derivative, should be zero, or approximately zero. So eventually when you reach the maximum, that sequence will be constant and will stay at the maximum. Okay, one quick detail about these gradient ascent is that these methods can converge to what we call a local maximum instead of a global maximum. So I'll just draw a little picture. So let's say you have a function which looks like this, and you want to find the maximum of this function. Okay, so let's say this is x and this is f of x. So here we do a one-dimensional example, but the same can happen in a multi-dimensional setting. So let's say you're at you start at this point here. This is x0. Then to find your x1, your next point is x0 plus a small adjustment times the derivative of the function. So here the slope is positive. So because the slope is positive, you'll make a positive adjustment to obtain x1. So x1 might be somewhere here. And then if you look here, the slope is again positive. So let's say maybe you make an adjustment. Maybe you end up here. So here this is x2. Here the slope is negative, so you go back a little, and then maybe at x3 you reach the maximum and you stop moving at this point because the derivative is 0, and then x4, x5, x6, etc. will remain at the same place. Okay, but here using this approach converges to what we call a local maximum instead of the global one. So the global maximum, which is the true maximum of the function, would be here, but this approach converges to what's called a local maximum. Okay, so this is some details about gradient ascent, but I don't want to spend too much time about them because this is not an optimization course. Please follow a formal optimization course to know more about these methods, but still it's useful to know a bit about them because we will use them to optimize our policies in this course. Okay. So, in our case, if we want to select action preferences to maximize the expected reward at the next step, then our next point So here the action preferences, they play the role of x in our in this scheme here. The next point, which is the next action preference, should be the previous one plus some constant alpha, okay, our step size, times the derivative of the function we'd like to optimize, which is the expected reward, with respect to the so this is x, but here in that case is the action preference. Okay, so this is what would be entailed by a formal gradient ascent algorithm. However, what's the issue with that formula? This is not applicable in practice because the problem is that this derivative is unknown. Okay, so we will solve this problem in a few slides, but before that, can we derive a formal expression for this derivative of expected reward with respect to action preferences? Okay, so it can be shown, and this is done in exercises, so we won't give the proof here because it's somewhat cumbersome, but still, it can be done, and you should work on this. I think for this exercise, the solution is in the textbook. So the first time you go through this, it might be useful to read the proof instead of try it because it's somewhat complicated, but you should nevertheless try to understand the various steps of that proof. Okay, so it can be shown that the derivative of the expected reward on the next step with respect to the action preferences can be written as follows. It's the expected, given your first t minus 1 place, of the difference between your next reward and your historical average for the next for all rewards up to until play t of this indicator minus pi ta. Okay, so this indicator, which is 1 if action A is selected at the next step, minus the probability associated with action A. So therefore, if we what we'd like to do to have a formal gradient ascent is substitute this expression here for the derivative of our expected value with respect to the action preferences. We'll like to substitute that in the previous recursive equation. Okay, so if we go back one slide here, that term here for the derivative, we just derived an expression for it, which is the following expectation. Okay, so we would like to do the following to have a gradient ascent algorithm. Next, for all actions A, next preference is the current preference plus alpha, some small constant, times the expectation of the difference between the reward at play t minus the historical average times this. So this is what we like to do. However, it's impossible to do that because expected rewards are unknown. Okay, so if we want to know the expected reward for the next step, it's impossible to know that quantity. Okay, so to perform a formal gradient ascent, it's impossible in practice. Expected rewards are unknown. However, instead of performing a gradient ascent, we will perform what we call a stochastic gradient ascent. So in a stochastic gradient ascent, let's go back one slide. This term is unknown, but what we will do is instead of considering this term, we'll replace this term by an unbiased estimate of this term. So how can we obtain an unbiased estimate of this term? Well, we can just replace the expectation with what's inside. So this ensures that we have an unbiased estimate because if we take the expectation of what's inside, it becomes this whole term here. Okay, so in a stochastic gradient ascent, we replace this rule by another rule where instead of having the expectation operator here, we simply keep what's inside the expectation. Okay, so we replace the expectation by some unbiased estimate of the expectation. So this entails having the following formula. It entails having the action preference for all actions A. Action preference at the next step is the current action preference plus, so this is what's inside the expectation, alpha times the reward obtained by at play t minus the historical average times an indicator, which is 1 if action A is the action that was selected at play t minus pi t associated with action A. Okay, so now this formula, we can apply it in our case because the rewards, they are observed. And the actions we've selected, we know at every point in time what actions we took in the past. So all these quantities in practice, they are observed. So this can be applied in practice to select actions. So this is great. This is an actual applicable formula to select action preferences. About stochastic gradient methods. Okay, so there's a whole theory worked out for stochastic gradient methods, and it can be shown under some suitable conditions that the stochastic gradient method will converge, will lead to an algorithm converging to the optimal expected reward. Okay, so it can be shown that as t tends to infinity, the action preferences will tend to maximize their reward. So eventually, the preference for the best action will converge to infinity, and the preference for all non-optimal action will converge to minus infinity. Okay, so there's a whole theory worked out for stochastic gradient methods and their convergence to optimal value. However, we won't discuss this here. This is out of scope. Okay, so this would require a lot of stochastic analysis, more formal probability notions. So we'll leave that discussion aside. But I just wanted to let you know that if you're interested in the theory of reinforcement learning, there's a lot to learn there, and you can look at the theory associated with stochastic gradient methods. Okay, so we have a stochastic gradient approach which leads to this formula, which is applicable in practice because at all time step t, all of these quantities are observable. So you can apply this formula instead of the regular gradient ascent, which involve expectations which are unknown in practice. So are we done? Well, the answer is yes, because this is exactly the formula we've shown in earlier steps. Okay, so this is where the formula we provided earlier for the update of action preferences come from. So this is the proof associated with the derivation of the formula. Okay, so this completes our the last strategy we proposed for the K-arm bandit problem. Now, just before we end this chapter, I just want to briefly discuss a generalization of the problem. So, in the K-arm bandit problem, we had a single state of the nature. Okay, so at all plays, the distribution of rewards for all for some given action is always the same. Okay, so for a given arm, rewards were IID. There's a generalization of the problem where you have multiple states of the nature. Okay, state 1, state 2, state 3, for example. And then, okay, let's put that aside. I'll describe that in the next slide. Okay, but so the regular K-arm bandit problem we studied is called a non-associative context. Okay, So to try to determine what the best action is, there's no observable state variable in that case. Okay, so there's no other information to help you determine the best action than previously obtained rewards. Okay, so previously obtained rewards is the only source of information to try to forecast the value of all actions in that case. However, there's a generalization of the problem which is called associative bandits. So, in that associative bandits case, before every time an action is performed, just before the action is taken, a state variable is observed, and then the distribution of rewards for all actions is assumed to be dependent of that state variable. Okay, so in that case, the problem, the K-arm bandit problem, becomes not only to select an optimal action, but now the optimal action might be different in the different states of the nature. So you have to associate an optimal action with each state of the nature. Okay, so maybe in state 1 it's the action A which is optimal. In state 2 maybe it's action C. In state 3 maybe the best optimal is action B. So here the problem becomes selecting a policy where the policy consists in selecting an action as a function of the observable state variable. Okay, so maybe this is abstract, but let's use a more concrete example for that. So let's say you have a slot machine, and every time you have to pull one of the levers, then there's a light that is displayed on the top of the machine. And let's say sometimes the light is red, sometimes the light is blue. And you know that when you have a red light, you have one distribution for rewards. When you have a blue light, then you have another set of distributions for rewards. Okay, so you know that the color of the light will influence the distribution of all rewards for the various actions. So in that case, the best action will vary according to the color of the light. So maybe for when the light is red, it's one action that is optimal. When the color is blue, it's another action that is optimal. So in that case, you have to find not only a best action, but what is the best action for each state. Okay, so this is a generalization of the K-arm bandit problem, which is called associative bandits. So you have to associate the best actions with the various states of the nature. Okay, so this is a nice generalization. This is known as contextual bandits in the literature because the best action is dependent on the context or the state of the nature faced at some point in time. Okay, so this generalization, I've explained it briefly. However, we will not discuss this one more in depth right now because we will see that this contextual bandit problem is a particular case of the more general reinforcement learning problem we will face in future chapters. Okay, so instead of considering the contextual bandits, we will consider even more general problems for which these contextual bandits is a particular case. Okay, so we'll stop the lecture here, and I'll see you for chapter 3 videos shortly. Have a nice day.